All right. For the last couple of weeks, we've been all about oxygen delivery, the cannulas, the masks, the entrainment devices. And the question underneath all of it has been the same one. How much oxygen are we giving the patients? This week, I want to shift that question just a little bit. A patient struggling to breathe, and the instinct is often just more oxygen, give them more oxygen, turn it up. But sometimes concentration isn't actually the problem. Something else is stopping that oxygen from doing its job. So this week, instead of asking how much oxygen we're delivering, we're going to ask what's actually blocking it and what can we actually change to fix that. Picture four patients coming through the door. On paper, all four might get written up the same way: respiratory distress. Look closer, and the physiology is completely different in each one. One patient isn't getting enough oxygen pressure down at the alveoli, the gas exchange surface. Another has gas trapped somewhere in the body, gas that will expand or compress depending on the pressure around it. A third has a narrow airway with turbulent airflow, a dense gas fighting its way through a tight space. And a fourth has high resistance in the pulmonary blood vessels. So blood isn't reaching the parts of the lungs that are actually ventilated. Four different mechanisms. Just turning up the oxygen might improve oxygenation, but in several of those patients, it still doesn't address the underlying problem. Different problems need different levers. Remember this from earlier in the semester. None of our equipment is magic. Every device, every therapy is really just us manipulating some physical variable, whether that's pressure, volume, concentration, or resistance. So this week, I want you to think of each therapy as a lever. Somewhere in the body, there's a variable we can push on, and the therapy exists to push it. Mm. We'll come back to that word, lever, more than once this week. Okay, so this is where I want to slow down because this next distinction trips up a lot of people. We've used FiO2 all semester. It's the fraction of oxygen in whatever gas someone's breathing. 21% in room air, maybe 40 on a mask, 100 on a non-rebreather. That's a concentration. Does that number by itself tell you how hard oxygen is pushing into the blood? Not on its own. Concentration and pressure are related, but they are not the same thing. So follow oxygen's actual journey: room air to the airway to the alveoli to the blood. Four stops, and we give the oxygen pressure a different name at each one of those. At the start, that's FiO2. Once the gas has traveled the airway and picked up water vapor, we call it PiO2, inspired oxygen pressure. Once it's inside the alveoli, it's P big AO2. Notice that it's P capital AO2. And once it's crossed into the bloodstream, it's PaO2. And that's P little a O2, so a lowercase. Notice how close those last two sound. P big AO2, P little AO2. One capital A, one lowercase a. Two completely different locations, two different numbers. And we're about to watch that number change at every single step. So let's walk oxygen down the staircase. Remember, at sea level, total pressure, annotated as PB, is 760 millimeters of mercury. Room air is 21% oxygen. Multiply those, and dry inspired oxygen comes out to about 160. Once that gas humidifies on the way down, it drops to about 150. That's PiO2. And we'll see exactly why on the next slide. But the alveolus PaO2 is dropped again, taking up space oxygen would otherwise occupy. And across into arterial blood, P little AO2 drops slightly further to around 95, a small loss from normal ventilation perfusion mismatch, meaning airflow and blood flow aren't perfectly matched everywhere in the lung. Eventually, you'll use the gap between what the alveoli should have and what actually reached the artery. That's the A to A gradient. We're not going to go deep on that yet, but that is coming up. Let's slow down on the first drop, 160 to 150, because there's a nice picture here. Think of the alveolus as a crowded room with a fixed number of seats, 760 total. Once inspired gas warms to body temperature, water vapor climbs into that room and takes 47 of those seats. That's not oxygen disappearing, it's water vapor now occupying part of the total pressure. So 760 minus the 47 leaves us with 713 for everything else, oxygen, nitrogen, all of it. We're not removing oxygen, we're just giving water vapor a seat, and every other gas has to share what's left. Now we can put an actual number on PaO2 instead of just estimating it using the alveolar air equation. It looks intimidating written out, but every piece is something we already covered. PaO2, or big AO2, equals barometric pressure minus water vapor pressure times the FiO2, or the fraction of inspired oxygen, minus the PaCO2 divided by R. So again, that's alveolar oxygen pressure equals barometric pressure minus water vapor pressure times the inspired oxygen fraction minus the carbon dioxide pressure divided by R. So PB is the environment, the total atmospheric pressure. PHO2 is humidification, that 47 we just subtracted. FiO2 is the oxygen we're delivering. PaCO2 is carbon dioxide in arterial blood. Since the carbon dioxide takes up room in the alveolus too, we have to add that in. And R is the respiratory quotient. We'll use 0.8 for this introductory calculation. You don't need to dive into the metabolism behind the number just yet. So this equation is really just telling a story you already know. How much pressure is available minus what carbon dioxide takes away. So let's run through the numbers one step at a time. Normal values, barometric pressure 760, FiO2 as a decimal is 0.21, and PaCO2 is 40, and R is 0.8. So step one, we will subtract water vapor. 760 minus 47 gives us 713. The pressure left for the rest of the gases, right? Step two, multiply by FiO2. 713 times 0.21 comes out to about 149.7. Basically, our humidified inspired oxygen pressure, same idea as PiO2. Step three, account for carbon dioxide. 40 divided by 0.8 equals 50. How much pressure CO2 is taking up inside the alveolar? Step four, we're going to subtract that out. 149.7 minus the 50 lands us around 100. P, big AO2, is about 100 millimeters of mercury, the number your lungs are defending breathing normal room air at sea level. And notice nowhere in this math that we use 100% oxygen. This is just room air. Okay, before you touch that calculator, we should be able to predict which direction PaO2, that's big A, moves. That's more useful clinically than the arithmetic. So FiO2 up, PaO2 is up. More oxygen going in, more reaching the alveoli. Barometric pressure up, PaO2 up, more total pressure available. And then if you have PaCO2 is up, or PaO2 will be down. More carbon dioxide crowding oxygen out of that same space. And barometric pressure is down, like climbing a mountain. PaO2 will be down too. Same 21% oxygen, but thinner air overall. So less oxygen pressure is actually available. So what happens at the top of the mountain? Barometric pressure drops, PaO2 drops with it, and a person can end up hypoxic, even while still breathing 21% oxygen. Here's one that I want you to stop and think on. Two patients are both breathing 21% oxygen, one at sea level, one at high altitude. Do they have the same inspired oxygen pressure? They wouldn't, because barometric pressure is different between them. Even though the percentage of oxygen is identical, concentration stayed the same, but the pressure didn't. Here's where we land at. FiO2 tells you concentration, P big AO2 tells you pressure, and that pressure depends on FiO2, barometric pressure, humidification, and CO2 all working together. Now take that mountain scenario and let's flip it around. Instead of going up and lowering pressure, what if we deliberately raised it on purpose? And that's exactly where we're headed next.